There we go. We're recording now. Pour all the information into your head. um, but just know, Dr. Ngana, he, if you need a place to start, yeah, well, I will say, and I think I said this before, like that middle test is can be the most difficult. The second one, even though it's cumulative, just like you're saying, you kind of have a feel for the most difficult stuff because that middle section is the most challenging information to learn. But now you have a feel for it. So the most challenging part of the class won't seem so challenging in terms of like asking those questions and yeah. So hopefully that but please, like Dr. Ngana has always said, focus on the lecture, the lecture slide questions. Like I think I told some of you this. I don't know why he didn't tell you all, but he made a very, in the physics 1 class when he was doing the review for him, he just like they were reviewing, and then out of nowhere, he just said, hey, make sure that if you're wanting, if you're trying to figure out, I mean, everyone wasn't doing so on the questions, I think. And so he said, make sure that, for the test, if you want to know how to do the best on the test, is the best place to start is with the lecture slides and with the clicker questions and the worked out questions. And he said, he told them, know all of them, and then also know them within, the longer mathematical problems, obviously you won't be able to do this with, but especially the clicker questions, all of them should be able to be solved within 2 minutes. Okay, so if you're working on a clicker question, like a good way to know that you're comfortable with it is it's one thing to be able to solve it. It's another thing to be able to solve it, within 2 minutes. And that's typically what he gives you for those questions, right? Is 2 minutes, and that's why. And so don't just try to answer the question, but make sure you can answer and understand it, within a certain time scale. I mean, that's just what he wants. If you were to ask him, like, Dr. Ngana, should I be able to answer these questions in a certain time limit? He would say, yeah, around 2 minutes. And he would also tell you, like, every question on the test shouldn't take you longer than 2 minutes. Like, he never gives you a long math question. So when you're, the questions that are always on the test are the ones that, they might be a piece of a long question, but they're not the whole question, or they're just, the clicker questions are, a very simple question that doesn't take you any longer than 2 minutes, if you've been practicing. Okay, so just keep that in mind. All right, because he just went into all this detail with the physics 1 class about that, and it's, he's essentially, saying, if you can use that as a baseline, and then, you can go off into the worksheets and look at the worksheets, because those are another good guide. He took away SAP. I think I told all of you, because of the way your feedback, it had a lot to do with your feedback. The class no longer does sapling. They don't even have sapling. They actually turn the worksheets in for points now. And so that's where he literally tells them, and that's still true this semester, even though you have sapling. But what you kind of have an advantage with sapling in terms of is if you get through all the clicker questions and all the worked out questions on the slides and all the worksheet questions, and not just being able to work through them, but you understand them and you can answer them within a few minutes, then hop on to sapling and start, quizzing yourself there. But I would kind of work in that order, and Dr. Dungana would tell you to work in that order. And remember, it's not just about being able to answer his questions. Make sure you can answer them in the appropriate amount of time. If you look at a question It takes you 5 minutes to answer. Try to, you know, go on, work on other questions, but then come back to that question and see if you can solve it faster. You're like, okay, I know what I have an idea for this one. Can I do it? Can I get there quicker? And then try it, see what you do. If it's, it's probably going to be quicker. And then move on, do a few questions and come back to that one and say, okay, can I do this? Can I do it even quicker? Okay. Because, and again, it's not, the thing is it's not about speed. What he explained in the class is that if you can answer those questions within 2 minutes per question, you won't feel rushed. You won't, have to, hopefully, or if you do have to guess, you'll have plenty of time to look at the questions you don't know the answers for. Because if you can answer the questions, 2 minutes per, you're gonna finish the test with an appropriate amount of time to be able to review things and all this other stuff. But if it takes you longer, the longer it takes you per question, the more that stacks up at the end. So that's just what he would say. I'm just letting you know. And he did make this speech to the physics 1 class. So you can use that as a guide as you're going through everything. Is look at those clicker questions. Look at those worked out questions from the slides, right? And then once you got those down, go over to the worksheets. Make sure you understand those, and then hop on sapling if you've done that. So, okay, so let's move forward here. Yeah, so it's gonna be 50-50. So it's gonna be 50. So first of all, it's gonna be 30 questions. Let's start with that. So out of 30 questions, it's gonna be 50-50, which means 15 questions are going to be based off the new information you haven't been tested on. 15 questions are going to be based off the information that you have been tested on. Okay. And, so that kind of gives you an idea of like how, in terms of the prior information, he has about 15 questions that he can ask you about the prior information. So all that stuff is going to get spread out. So just, understanding no problem. Understanding like what I always tell students for the cumulative test for Dr. Ngana is, look at the chapters of the titles of the chapters that we've given you, because the titles of the chapter are a good indication of what he's probably going to test you on for that section. So if it's called electric force and electric field, then that's what he's going to test you on for that section. So make sure you understand everything about like electric force in the field in terms of generalities. But there's a lot of details that we can throw in there that we do, but some of it is just like application stuff like this, where there's just like overall. And also please keep in mind, for everything up to RLC circuits, you're using Newtonian physics. So one thing he's really going to also be trying to get you on with the first bit of information is, even though he might be talking about electric field or magnetic field, he's going to still be like, he's going to be trying to test you on Newton laws. Like there's going to be a couple of questions, or if not more, just like in different ways testing you on Newton laws. Maybe the first one, maybe the second one. All right. So that's another good indication of how to study, because at the end of physics 2, we want you to have a good idea of some things, and the Newton laws are some of the most important stuff. The other most important stuff would be like energy things. All right, so anything to do with energy, kinetic energy, work, all that stuff, and momentum, those are all really overall general topics that came from physics 1 into this class that he's just going to be generally trying to test you on as well. So that prior information, he might test you on the right hand rule for magnetic force, but then he also might give you a situation and say, what would be the equation? He might not have you solve for anything, but say, hey, what would be the equation for this particle moving in this magnetic field, right? So All right. So this review is gonna cover, he kind of jumped around there at the back end. But we're gonna talk about light, and most of it's about light. Actually, even towards the back, we're still kind of talking about light in a way. Because light, essentially, light is electromagnetic energy. And was there any more questions before we get going here? I'm good. Okay, just making sure. I kind of jumped into that, and then I was like, oh, I hope someone wasn't waiting to ask a question. Okay, I'm just making sure. So light. When we think about light, we think about visible light, okay, which is fine. But keep what the first chapter that we're starting with, and again, we're not gonna. He barely talked about it, so I don't want to spend a lot of time on it. But is that the idea is that light is a spectrum, right? And it's a spectrum. It's part of or visible light, right? Is part of the electromagnetic spectrum, right? So, the way you think about visible light, you should, I guess what you should take away from that is the way you think about visible light is the way you should think about UV, and the way you should think about X-rays, and the way you should think about gamma rays and radio waves. Like a lot of times when we talk about photons, a lot of students think that that's only, or maybe before they start the class, right? Maybe not now, you probably have a good understanding of it, but we think that photons are just have to do with visible light. And like if you were to hear the word like radio waves and say, do radio waves come in photons? You would have said, no, radio waves are just a wave. They don't, no. But what did you learn this semester? You learned that no, radio waves are like visible light. They come in photons. Radio waves, they come in photons, packets of energy, just like our visible light comes in terms of like these little packets of energy. We could think of as photons. But at the same time, and that's the thing that we were trying to teach you at the end, that these waves are these particles, and especially light's the best example, is both it can behave both as a particle and a wave, right? So we know that visible light isn't just we could think of it as a photon, which should be thinking of it as a particle, thinking of light as a particle. But then we could think of light just as like this constant, electromagnetic wave that's just moving through space, right? And so uh, uh, just keep that in mind, like, and we'll come back to that towards the end. But that's the whole idea is, things can be, particles and waves. So we could think of that, right? The electromagnetic, like if I had a specific like, let's say like this is the red is the electric field, the magnetic field, right? Well, we could think of this, and this could be, of any, this could be an electromagnetic wave of any and anywhere along the spectrum, right? But what the way what I'm essentially saying, and what we're trying to say at the end of the chapter here, is that you could have this wave, or you can have this like little packet where like that would be the photon of the electromagnetic wave, right? It could be this little ball, this little packet of an electromagnetic wave, right, which could act like a ball and it'd act like energy. Or it could just be, right, and this ball could be moving, in this direction. Like if you threw a baseball, right, then the photon would be moving this way in terms of this ball. Or you could think of it in terms of just the wave itself, just propagating through space. Okay. And the thing, he talked about some things in this chapter, so please know them all, but a lot of the things he talked about were pretty straightforward. The one thing that I wanted to just make sure you did understand from this chapter is that the equation that goes with an electromagnetic wave, because if he were to ask you something from here, it could be something as simple as the intensity solution. Is really straightforward. But if he asks you to write an equation for this electromagnetic wave, I know that's where things could be a little complicated. So now he could ask you to write the equation in terms of E or B, but no matter how you write it, like the generalities are going to stay the same. Okay, so like in this case, in this case, right, this would be Y, this would be X, and then like, coming out, that would be like Z, right? And so we see that the electric field right here is oscillating in the Y direction, positive, negative, right? And we see that the magnetic field is oscillating in the Z direction, positive, negative, okay? But then we can look at the wave in general and say, okay, it's propagating, this velocity is in the X direction, right? It's moving in the X direction. It's moving from the positive, from the, I don't know what we could say, from the left to the right here. Okay, so in order to write an equation for this, it's, again, not difficult. First of all, again, it's either going to be the electric field or magnetic field that we're asking you to write the equation of. In this case, we'll write it for the electric field. So we know the electric field is in the Y direction. Okay, and so just like any equation is a function of time, which should be on here as well. I don't know why. I don't know if he's given it to you that long, but it should be. So I'm going to put it all in there because this is essentially a function of X, Y, Z. But since it's only in the Y, X and Z are going to be equal to 0 in time. So like, that's essentially how you'd want to write it, because it's a function of all those things. But then we can look at the equation and see some things. You'll see what I'm talking about here. So I'm trying to think if like, anyway, the first thing we want to start with is amplitude. Okay, so the amplitude here would be the electric field, be the magnitude of the electric field, right? And that would be we would be using the maximum points of the electric field, because we're going to write this equation as a function of this electric field. And so, E naught would essentially be that maximum. That's what we'd be calling that. And then we could we could look at any point of this equation. We could write this in terms of sine or cosine, depending on how it looks, based off where I have it at the axes here. It's a cosine, right? So, and then we have this, again, he gave you a question about this where he had everything filled out. So I don't think you're going to, again, you don't write anything out on the test. It's just really about identifying the correct equation here. So more than likely, I was just trying to think about what's the best way to write this for you. He's going to have this written like in terms of EY, because he's going to give you like a picture like this, and he's going to want you to recognize that like this is the electric field in the Y direction. So that's probably the best way to be writing this. And then this equation's telling us a few things. Oh, we understood where I got the cosine from. I kind of showed you right here, but I just wanted to make sure. Right, cosine starting at a max and going to a minimum essentially at that point. So it's a cosine function. Good. Essentially, it's not gonna, I'm trying to use that picture. It's gonna be pretty, with Dr. Ungana, it's gonna be pretty straightforward. It's gonna be, he's gonna give you a wave, right? That's gonna, look like this, or it's gonna look, like this. And so, you'll be able to, this would definitely be cosine, right? It'd be very obvious. I'm trying to use that awful picture, which I shouldn't, right? Where he would have this electric field as a function of time. Yeah, sorry about that. I shouldn't have done that. And so it'll be very clear. You'll be like, oh, this is obviously like a sine function here, right? One thing he may do is like he might have like this wave here. I don't want this to look too sloppy. He might have this wave here, but then what he might do is he might say like, what's the so this is the wave he gives you. But then he might say like, what's the equation for at this point? So at this point, it starts as a sine wave, right? But if I were to write the equation starting at this point, what type of wave would it be?
What would be a cosine?
Exactly. So like that's as tricky as it can get. Okay, but I mean it's going to be very obvious whether it's sine or cosine, but he could do this and say, oh, it might give you this graph, but say like, at the point marked, he'll have it marked or something. It'll be obvious like where, what's the graph for that point? Well, at this point, right, you can see it's gonna, it's a cosine at that point, even though it started at sine. That's tricky. If you're like, that's not tricky, then good, because that's about as tricky as this can get. And then the only other thing that I want to point out here, so first of all, we right, the electric field is in the y, right? So the equation is telling us that, but it's also telling us direction of propagation by this. So like if the that I guess that's another way to check to make sure like this is correct. If the equation's moving in the, if this was the y, like for some reason this was the y, he said it was, like the v was pointed in the y direction or something like this, I don't know, then this would be y. But then the electric field couldn't be in the y direction, right? The electric field would have to be in z or x. Actually, it would probably be an x, and everything's perpendicular here, just like in the magnetic field with magnetic force and velocity and stuff. Like everything was perpendicular there. It's the same thing here. If you can see that, you can see that the electric field, the magnetic field are perpendicular to propagation. So just know that that's what that equation, because again, he's just going to ask you to identify the correct equation. So just know that, like, he's going to show the direction it's moving, and you want this part of the equation should reflect the direction of propagation. So that's why, since this is moving in the x direction, it's written in terms of x. Does that make sense what I'm saying? It'll be represented there. Okay. Possibly, but it would be identical except for what? If he said, what's the equation for B? You should be able to write it with like all the information you have already, because it's moving in the x, this is in the y. So the B is going to be in the what? The z, right? And then this would be B naught. The nice thing is that, the B and Z are doing, again, you can't see it here, but the B and Z are doing the same thing. So, when the I'm just gonna have So, you know, as the X or as the electric field does this, the the B is also growing, but it's growing towards us, right? So they both work the same way. So if this is sine, the B is going to be a sine. Do you see what I'm saying? Like they're not out of phase. If they were out of phase of one another, then one would be sine and one would be cosine, right? But they're in phase with each other. So if one's sine, the other one's sine. So you know, you like, does that make? I'm just saying, like we know how to also write the function here. So if this is cosine, then we know this is going to be cosine. Besides just, you know, he could just ask you for magnetic field and you would do it the same way if he didn't have the electric field. But and then this would all stay the same way actually. So does it? What does this middle sign mean? Yeah, K is what we call the wave number, and so so K. I mean, there's a couple ways to write K, but we typically refer to it as this. I believe K is also omega over. Hold on, I have it somewhere here. K is also omega over V, but I don't know. You know, you might not. We use this, right, where V could be the speed of light, but and it would be in this case because it's an EM wave. So keep in mind, anytime you have a V for these, that's always going to be the speed of light. And there's also an equation, you know it, that connects the E and B. Like if he gives you the E and asks you to write the B equation, like in order, you know, and he would give you this number here, that number would be there for E naught. But you could solve for let me write this a little bit clearer. You could solve this for, like, this is E naught over B naught. So if you know E naught, right, you could solve for B naught this way. Or if you know B naught, you could solve for E naught. You know, I'm out of space here. Like this way. Does that make sense what I'm saying? Like this is the equation that connects the amplitudes to one another. So if you know one amplitude, that this equation can get you the other amplitude if you needed to write it. Does that make sense what I'm saying there? Okay. And then so that's the wave number. And then we know, like, we know omega, like omega could be written a couple different ways here too, right? It could be 2 pi f, or it could be written in terms of period. I mean, you could write omega a lot of different ways, I guess, if you wanted to, but like these are typically, so what you see here, typically the ways that I see K and omega written for these equations. Or he might, essentially what I'm saying is, like, if he had to put numbers in here and you needed omega, he might give you frequency, right? Or he could also give you period, and you could get omega. Or if he gave you omega, this number, you could solve for period, right? So kind of that back and forth. I don't know if he goes that far with these equations. I just know this is the most complicated. This is where students find, you know, the most difficult of that small little section. It's a small little section just talking about an electromagnetic wave, right? And so yeah. So that's what I'm saying down here. But back to my original question, which was, what is this? What's this sign mean right there? What does that sign mean? So in this case, it's negative, but like, what if it's positive? It could be positive. Good. It's the direction, like in terms of like positive or negative. So we know, good job. So we know it's moving in the X direction, but like, is it moving right in the positive or negative X direction? This equation has to be able to tell us that. This is like the equation, right? Right, as a function of time. I at least gotta put that in there. For an electric field and a magnetic field, right? So do you remember, because we actually showed you this in physics 1, how does that work when that's negative? Oh wait, I think, yeah, so I got it from Megan. So it's moving in the positive X direction if it's a negative sign. Exactly. So it's always the opposite, right? So if this is negative, if you see the negative sign in there, that means it's moving, right? It's moving in the positive X direction. Okay, if that's negative. Okay, that's how we have to think. And if it's positive, if this is a plus sign in here, because it could be a plus sign. It's just this is moving. I guess I didn't indicate that. I assumed that was positive X, but this is moving in the positive X. So I wrote that. I didn't. I wrote it as that's why it's negative. I forgot to show this was positive X. But so that's why it's negative. But if it happens to be positive in there, then that means it's moving in the negative direction. Okay, cool. Everyone good with that? Okay, so let's move forward onto there's more about light. I just wanted to make sure we understood this equation, but this is really everything you need to know. Okay, and like I said, on the test, it'll be very clear. It's not going to be that messy picture. So it'll be very clear if it's sine or cosine. In fact, I think he gave you a clicker question, so you can look at that question and see how he would give, like he gave a picture on that question. I believe, I don't have it. It was like a new question, so I don't have it. But I think Levi showed it to me. So just know it's there. Okay, and it's just one clicker question, but again, I just want to make sure we understood that. But there's definitely a lot more to talk about. Okay. So everything here moving forward, all this stuff, including the new stuff that he talked to it. So everything from what I'm going to talk about here, all the way until the last stuff that Dr. Dungana talked about in class, which we should be able to get through. You should know it works entirely different than anything you've done in physics. Okay, it's going to work actually a lot more like a typical like science class where you memorize the concept. So if we give you a concave lens, you should know everything that goes with that concave lens. Nothing's ever going to change. We're not going to give you some freaky situation where all of a sudden the object is P is not positive, right? It's only positive if it's virtual, and that's it. Nothing changes. Like it's just these things to memorize, to know. And that is, please listen to what I'm saying because it's very important. That is true for not just the thing I just referred to, but everything else. So it's just about memorizing this information, which is completely different than everything in physics. Because normally it was like, draw a free body diagram, write an equation, or if it's in a something oscillating, there's going to be some equation as a function of time or something like this. There was all these things that essentially what you learned in physics 1 you brought into physics 2 to be able to solve all those problems up until now. But then it flips because it gets real. The math, first of all, gets pretty high level, so it's hard to do a lot of it. So it turns into this idea of like, okay, yes, there's going to be some equations here, but the equations are going to be very simple. Like all this optics stuff, no matter what we're talking about in the optics, we keep using the same equations over and over. The equations don't change. it's like the same one. Like we just keep using it. We just have to make sure that we understand, you know, how we're using it. It actually doesn't change each way that we're using it. I guess what's important is to see how that equation applies to each situation. That's all that's important. But it's going to be a memorization thing. A lot of us have, if you've come to SI this past week, and we've I'm going to limit it, so hopefully no one tomorrow asks this question, because I'm going to say let's try to do it at the end. But twice, we've discussed the the interference and diffraction worksheets. But at, at the end of the day, that stuff, it's just memorization. It's just making sure you know the pictures. And your pictures, are the ones in the book, do a great job, but also the ones in the slide are great. But again, it's kind of hard for me to replicate all that stuff. A, because a lot of those pictures are done with the computer, but B, because it's really just memorization, and it should be. Unfortunately, I really hate saying that, but that's what a lot of this stuff turns into. And what I've seen, this happens so much with all this stuff with light and relativity and quantum mechanics, is that because physics was so challenging up to this point, students want to make a lot more of that stuff. They're like, we kind of want to make it like there has to be something more going on here. This has to be harder, when it's like, no, it really is just because the picture says so, or just because the book said so. Like it's not as challenging as it was before, which is kind of like a hard thing to get over. Some of you know what I'm talking about. Because we've ran into that a lot. We ran into that first with like the lenses, where it was like, Carl, tell me about the lenses, teach me about the lenses. I was like, I can, but I'm telling you, you need to go memorize that stuff I gave you, because I'm just going to keep telling you the same thing over and over, and you just got to memorize when something's going to be, when P's positive, when P's negative, and it's based, right, that's not based off something I said or a situation. It's based off of the overall idea, which is what you need to memorize. Anyway, you don't know what I mean. We're going to talk about it now, but I guess another thing I'm trying to say is that it's kind of challenging to go through some of this stuff because of that reason. Okay, so, and everything we talked about, I think he moved really slow through this section, again, because he wanted you to really understand. But I think because of how slow we moved, there was a big separation between all the information. But the light stuff actually all goes together. So everything we're about to talk about now, all the way through, the thin films, that stuff, it all goes together. It's all like one story. Okay, so the stuff we're talking about now, all the way through thin films. As you're studying it, you should have it all together as one giant picture in your head. We're trying to tell you a story there. And this first stuff we talk about is what we call geometrical physics. We use just like the angles to look at light. And then when we start talking about like double slit, we're still just trying to look at what light's doing. We're just trying to look at the physics way, which is in terms of wavelength and how waves interfere and different path lengths that waves take could end up making them be out of phase as well. Okay, so I don't want to spend a lot of time on it, but I think it, because like I said, there was such a distance between this information, I think this got lost. But something that we told you at the beginning, and also it seems so simple, I think, is the issue. But if there's a wave, first of all, one way to draw that wave, like moving out, right? Like let's say I drop a rock right here, right, and there's this wave moving out, is that's how the wave would like actually look. We'd look at it, right? And what we know, what the one thing that you should kind of take away from this idea, because these are the same pictures you're looking at with interference and diffraction, is that from one wavelet to one wavelet, that's one wavelength. Okay, that's the only thing you should really be taking away, but it's actually kind of important when you go to look at those pictures, because if you don't know those distances or talking about one wavelength, then when they start to interact, you don't and one way he talks about it is like peak to peak. Like another way to look at it would be if I did have some interfering like waves here, then like another place to see a full wavelength would be peak to peak there, right? So this wavelength right here and this wavelength right here, they correlate to each other, but this is of a different wave, right? We know that wavelengths are, we can measure wavelengths from peak to peak, so we know that distance right there is peak to peak. But that's the difference between wavelength between two different, or that's a full wavelength between two different waves, right? Where here in this situation, this is the same, this is the same source, same wave moving out. So is that making sense what I'm saying right now? If not, the big takeaway is just know between each wavelet, just like we say from peak to peak is one wavelength, is also going to be one wavelength. Like that's the thing we were trying to show you here. And then essentially what we showed you is that, we start to look at these as just straight lines. And then eventually what we showed you, and the reason why we showed you all of this is just to show you that like when we go to talk about this light that we're about to talk about, we're going to be drawing this ray, but you should know that this ray is representing these half circles. You should know that these are there, right? But when we draw this ray in terms of just this arrow, we're representing this arrow in terms of direction of propagation of these waves. Because the reason why that's important is because we go back and forth. Some of you who came to SI and we've been working on this problem with interference and stuff like that. I'm sure you're understanding what I'm saying when I say you have to kind of go back and forth between this idea, because he gives you this arrow and you have to kind of know, okay, what's that arrow telling me? It's telling me about these wave fronts, right? These are what we call wave fronts, right? And these wave fronts, like the difference between each one of them is a wavelength, right? Which is what we're saying here. And essentially, right, like there's one wave, there's another wave, right? It goes from, that's one full wavelength right there. In terms of like the peak to trough idea. Okay. So I'm just focusing on this because I think that, sometimes this gets lost when we start talking about other things. So just don't forget this whole idea. Okay. And so let's move forward. So the first thing that we talked about here was Snell's law. Okay. And Snell's law was just really trying to show us the ideas of how light interacts with the surface, right? And what were these things teach? Can anyone tell me, like, what was Snell's law like trying to describe? So Snell's law was trying to describe how light bends from one medium to another, but okay, good. That is answering my question. Yes. But what, like why? What was the point? Like what did we know? Like what were we trying to I'm trying to think of a good way to say that. It's a property, which it's not a mathematical thing really. It's just this this property that we were trying to dive in deeper on, I guess. I don't know. I'm trying to.
Refraction, refractive indexes.
So it was right. It was trying to put all that stuff together. That is also correct. Essentially, let me just say the answer, because I don't know. Maybe I'm not asking it the way that, because you are all giving me really good answers, and they are related. So we know the behavior. The thing that you should have in the back of your head as we talk about all this stuff that we're about to talk about is the actual behavior of light. Which, what do we see? We see some light reflects and some light transmits, right? And this is the idea we have to take in at remember this stuff ends with thin lenses. And remember, with the thin lenses, you have to you're drawing pictures like this, and you're saying, okay, this is pi, and then you do another one, and you see, right? You end up coming back to the first thing you talk about, which is this idea of when there's a surface, any type of surface, right? Here, yes, all the things you're saying are so awesome. Like here, right? If we're going from a small index of refraction to a large index of refraction, you now know we call this like a hard boundary, right? So it causes certain things to happen, but there's still going to be some transmission. That was the main first thing to really see here, is just like, okay, what are we trying to understand about light? Like when we see light shine in, does light just hit the top of the surface of something? And what you should be seeing is, no, it doesn't. Light always transmits and reflect. It does both. It can transmit and reflect. But remember, reflection has to do with absorption and then re-emission, right? So all these, all this stuff is made out of and this also starts our journey into quantum mechanics, right? But it's all made out of atoms and things like this. So like when the energy, the light, the electromagnetic energy comes in, it excites the matter, right? And some of that matter is some of the energy, some of the light that's coming in, some of it's going to be absorbed and then reflected back, essentially absorbed and then transmitted. That's what reflection is. Reflection isn't, if we think of electromagnetic energy as a ball, then yes, you can think of reflection as just like the photons are bouncing off this surface right here, right? But if we think of it in terms of its wave behavior, which is what we're trying to talk about right now, then what's happening is that this surface has some atoms that are gonna, it's not gonna be, this, let's say this is sunlight. So this has like all the wavelengths coming in, right? All for the whole spectrum from one end to the other, right? And so this surface that it interacts with, some of the atoms in that surface are going to absorb some of that energy and spit it back out. And some of that energy is going to move through deeper and it's going to interact with atoms deeper in, based off what's going on. I don't think we get that deep with you, but that's the idea that you should see, that we're trying to, that's where we were trying to start this whole idea, where we have this incident ray, right, which is going to be some light that's like coming in, right? And when that incident ray hits some sort of boundary, that boundary could be water, that boundary could be a piece of wood, that boundary could be, moving from a certain amount of air to just a denser amount of air. Okay, but when that happens, if it's in the same material, then it's just moving through. It's just an incident wave moving through. But the minute it hits a boundary, there's always going to be some transmission and some reflection. And again, why is this important? It's important for now when we talk about Snell's law, but it's also important when we get to the end and we start to talk about thin films, because we talk about these waves that are bouncing off, and then some are absorbing through and then bouncing off, right? And we talk about them having constructive and deconstructive interference. And it's like, where did that come from? Well, it came from this. It came from this stuff at the beginning, right? And we have this transmitted ray, and we have this reflected ray, right? So that's incident ray, reflected ray. What can I write on this thing now? Transmission or transmitted ray. And then the appropriate angles that go with it. Now, please remember, these angles are always measured off the what? I think you know this, but I'm asking because this is typically the stuff that you should know already. Always measured off the normal. Absolutely. Okay. So if we give you this angle, great. Just subtract this angle from 90 so that you have the angle that you need from normal, because that's the angle that we use in the equation, right? But it's also the angle that we use to measure this stuff. Okay, so keep that in mind. But it's never from the surface. It's always from the normal to the...
And is it also the angle that we get when we calculate it? That angle is related to the normal, not the surface.
Right. Absolutely. Like these are going to be the... So when we write the general equation out, good. Yes. Hold on. Let me write this. And then this is incident ray. Right. And then we know that these are all incident angle, reflected angle, and then transmitted angle, right? So Snell's law just connects it. So why doesn't it look, let me ask you this, why doesn't Snell's law look at the reflected ray offhand? We can look at, sometimes that reflected ray becomes really important. But why at the beginning are we interested in just the incident ray and the transmitted ray? So if we write out Snell's law, it's going to be Ni, which is going to be like in this case, if this is the incident, if we're calling this the incident ray, if we're calling this the incident ray, then this would be the incident index of refraction, right? And then it's, you know, sine theta incident is equal, and that theta incident is this angle right here, right? And this is N transmitted. And then this right here is the theta t. Okay. So yeah, like when you solve for what, like either one of these angles that you're solving in here, like this is that angle. This is that angle. So it is the angle off the normal. Like that's what the angle is in there. That's what's measured in there. But like I said, you could always write this as like 90 minus like this. We can call that phi, right? Because that could also be written that way. But the general way is written like this. And so Snell's law is just trying to connect what's going on with how the light bends as it moves from one medium to the other. Why? Because in this particular situation, this angle, what you should know is that the incident angle is equal to the reflected angle. Okay, they're always gonna. That's like the law of reflection, right? Like the law of reflection for mirrors, right? And all that stuff is that angle's equal, right? So the reason why Snell's law is not looking at anything is because, well, these angles are equal. There's nothing to hopefully there's nothing to calculate because those angles are equal, and so are the, you know, if this was R here and this was R, this angle would be the same as this one. But then this right here, even though this is R, and R is Ni, it's also equal to 1, right? They're going to be equal to themselves. Even if you wanted to solve for this angle, you would put that in here. And the Ni and the Nr would be equal. They both have the same index of refraction, right? So that's why we're not looking at the reflected angle can become important, right? If we're looking at polarization or total internal reflection. Sorry, that's what I was thinking. Not polarization, total internal reflection. Well, it works in terms of polarized too, but total internal reflection, right? And so that's when that reflected angle becomes really important, is for total internal reflection. But for this general case, it's not. It's just, we're just trying to describe the relationship between the incident ray and angle and the transmitted ray and the transmitted angle. All right. And so let me just ask you the concept here. I can't, it's not, we can draw it, but it should be something that you should already have in your head. Because I believe this stuff was actually on the second test as well. So you've actually been tested on this. What is so if we go from a small index of refraction to a large index of refraction, then what happens to the angle of transmission when compared to the angle of incidence? Does it get smaller or larger? If we go from a small index of refraction to a large index of refraction, what happens to the angle?
It goes from a bigger angle to a smaller angle.
Good. It gets closer, right? Yeah, it gets closer. And then what if it goes the other way? What if I go from a large index of refraction to a smaller index of refraction? What happens to that angle? The transmitted angle. Yeah, it gets larger. And remember, when we say increase or gets larger, it increases from the normal, right? Right. So it gets closer to the normal or gets further away from the normal. So if you go from a small index of refraction to a large index of refraction, that the transmitted ray is going to get closer to the normal. If you go from a large index of refraction to a small index of refraction, then the transmitted angle is going to get further away from the normal. Okay. And that's the underlying concept. Like if you start putting numbers in here, right, that you start to see. Okay, but that's the overall idea. So this started to just get into a few. I forgot to ask you, or just show you, I guess, or just remind you, I guess. Hopefully you know that the index of refraction, right, is is just the difference. I guess the other concept here to remember, it's easy to move past this because it's not that tricky, but right, is that also what happens is that the speed of the light slows down, right? If it goes into from a small index of refraction to a larger index of refraction, the speed of the light slows down, and that's actually what makes it bend. Part of what makes it bend, because it tries to find a shorter path through the medium since it slows down. It doesn't want to. It wants to stay at the speed of light. It doesn't want to stay slow. So it tries to find the shorter path through the medium. So it gets closer to the normal to increase it. It's shorter. Anyway, that's what's happening there. And so the index of refraction is just the difference between the speed of light, which is how the light moves in a vacuum, versus this is the speed in that particular medium. And I think you use this index of refraction equation in a lot of different places, but this is, I think, where we first introduced it to you and saying, make sure that when we talk about an index of refraction, it's just not, this number. It means something as well. It's just the difference in the speed of light. Okay. And then, so there was two ideas that went along with this. Again, not to spend a lot, there's no reason to really spend a lot of time on it. Just make sure that you understand. The first thing is the total internal reflection. Okay. And essentially what's going on there is, we start with the same, we start with Snell's law. Okay. But what we do is we a picture. So we have, right, this incident ray and this transmitted ray. And what we do is we play with this angle right here. So we move this up and down, right? Kind of change the angle, get it closer to the normal, further away from the normal. And we play with that until this, the transmitted ray is 90 degrees to the normal. Okay, so you play with this. And when you find that angle right here, so this is going to be, let me write that in a different way to make more sense. This is going to be 90 degrees, but that's going to be the theta t. So this right here, okay, or the transmitted angle. And then this right here, right, you're playing back and forth with it, which is the incident angle. But when you find that angle where this is equal to 90, or the transmitted angle is equal to 90, that's what we call the critical angle. Okay, and so we just this equation just I mean, you know, sine 90, because that's all we do is put 90 in here, right? That's equal to 1. So this equation essentially, right, turns into this, where we write this theta as the critical angle, but this is still like, you know, particular index of refraction, and this is particular angle of refraction. And I always write it, because I think in your book, and maybe even Dr. Yongana, I always write this in terms of incident and transmitted always, but you might see like 1 and 2. But keep in mind, like 1 always has to be the incoming angle, right? And anytime you have the incoming angle, doesn't matter what section we're in here, that's always the incident. I mean, you can call it N1, but that's always the, you know, a good way to, you kind of practice this concept as you work through this, is to remember that, like, hey, if it's the incoming angle to a certain boundary, right? This is the boundary here, right? Where we have, you know, again, 2 index of refractions, right? And we have, you know, it's coming into some boundary, that's going to be the incident angle, right? Even if there was another boundary up here that, like, that could have been the transmitted ray, but it's going to be the incident ray for the next boundary. Okay, so, and that's why that gets a little complicated when we talk about thin lenses, but hopefully when you hear all this together, you'll be like, oh, that's what's going on. That makes a lot more sense. You just got to hear it all together. And so wait, erasing that. So when that becomes 90, right, we essentially end up with this equation where this theta, which is still the angle from the normal, is just what we call the critical angle, which is this angle right here. And then, you know, Ni, I think I just explained what Ni and Nt are, so we know what that is. So you know, I don't know what he might ask you to do with this, but this is for total internal reflection, okay? And this is the angle that gets you total internal reflection. So essentially, what's going to happen is that there's not going to be any transmission. Essentially, everything that was coming in is going to be reflected back out. Okay, but again, these ain't, because of the law of reflection. Because of the law of reflection, you know, these angles are still the same. Oh my goodness, this thing is going to drive me nuts. Even though it doesn't look like it, they're the same. I need to be a little bit more accurate with my picture, but they are the same. You know, that never changes. That's one of the laws of total of not total internal reflection, but reflection in general, is that the reflected ray is always the same as the incident ray. But what's important here to understand is that there's no transmission. Okay, because everything, and this is the idea that we use for, I guess why that's important is, like, you know, when you look at those slides maybe or something like this, he talks about he might, I don't know if he does, fiber optics and stuff like this. So, like, you know, we need to keep the information in the fiber optic, you know, in the signal, and that signal's in the light. That light that we have going through the fiber optic cable, right, holds the information, holds the data for the internet, right, or your cable. And so if you lost some of that data, on the way to your TV from where it's from wherever it's coming in at, then you're not going to get a signal, right? So you got to make sure that the signal that's being sent to you, from the source, is the same signal that reaches you. And so how do we do that? With total internal reflection. And so anyway, okay. I'm just trying to make sure this isn't boring to you. So the 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 other thing that we can apply here is polarization, and I would say, like, this is probably the cooler one. Um, so this is talking about, why is it cooler? Because I think it explains a lot of things that go on in and these numbers are irrelevant. I'm just trying to go from a small to a large. Um, uh, uh, a lot of this stuff can describe like some of the stuff we see in nature, or stuff like this. But this right here, this is polarization. So what we can see is that, like, surfaces can polarize light. And what does that mean, by the way? If I were, let me ask you that, maybe to kind of get some juices flowing in you. I haven't asked you a question. Again, a lot of this stuff is just memorization. It's hard to kind of, but like, does that radiate with you in any kind of way? So first, let's just write the equation down here, and then I'll explain the concept, and then we'll move past this. It's just, so polarization. It's just, have some idea, and I think we've talked about it a couple of times in class. But anyway, here is essentially let me ask you this to try to get some practical value. Like, you've seen, like, your sunglasses. They say they're UV polarized. Maybe that might help. What the heck do you think that means? Like, when you read that, I'm sure you probably wanted to buy sunglasses that are UV I hope so. That'd be a very smart idea to do. Um, uh, what does that mean when they say it's UV polarized? Yeah, yeah. Essentially, we the UV light is so you could think of this, right? You could think of this as the UV light, right? Like, this surface right here is your sunglasses. I don't know how to draw that, so I'm not going to draw it. But let's say this is the surface of your sunglasses, okay? And then this would be like all the, like, your eyeball would be here, right? And so this would be all the safe light, anything that's safe, right? So we polarized it, right? We've 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 kind of, one way, it looks like we're filtering it, but essentially we've separated it, right? We've taken the light and kind of separated it into its parts, right? That's like the best way to probably have the idea of polarization here. Yeah, you're right. Like, we can use the idea of polarization, like we filter out the UV, we get rid of it so that all that comes through our eyeball is the safe light, right? But how did we do that? The surface that we had here, it's separate, right? This was sunlight, right, coming in, right? But then some, it hit the surface of your sunglasses. The UV reflected back out from where the sun was coming from. But the safe light came through, like the visible light and stuff like this, right? So 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 yeah, filters, but you could think about it. All it did was take the sunlight and separate it into its uh kind of its pieces, because the sunlight had the UV light in it. It had the safe light in it. Okay, so that's what we mean by polarizing. This angle between here, like there's a way to derive it, right? And it has to do with that angle uh, uh, being equal to 90. But don't worry about that. Okay, that's not the thing to focus on. The thing to focus on is that, again, it has to do with the angle of this light, and this angle ends up being the angle we call Brewster's angle. Okay, and then again, to write the equation, again, this would be incident transmitted, nothing. Again, you could use 1 and 2 here as well. Okay, now this is, again, it's written a little bit different because of the way we derive it, but don't worry about that, because he just gives you this equation. You should just know what it means when you see that B there. And so that B has to do with the angle of like, that's the angle that's going to allow you to filter the light. Okay, and then this is transmitted. Okay, and then typically, they might ask you, like, what's the angle of polarization, and that would be Brewster's. Okay, so that's what's going on there. How else does this work? Do you know why the sky is blue? It's because of this. Did you know that? So this is why the sky is blue. So what happens is, like, the atmosphere of the Earth, what it does is it polarizes the sunlight, and what we call this scattering. Essentially, the atmosphere, it scatters the light, and what happens, it has to do with the angle that you're at. But what happens is that when light gets scattered, essentially in terms of sunlight, it gets scattered in terms of blue wavelengths and red wavelengths, which should give an indication of, like, oh, hey, sunsets are red, sky blue during the day. And polarization only hits those two, only when the atmosphere polarizes sunlight, it polarizes it in terms of those two wavelengths, in terms of the blue and in terms of the red. And that should start to correlate things to you. So what happens is that as the light moves through the atmosphere, it starts to filter out through polarization, right? But we call this scattering, the blue light, because the blue light scatters, like, it's like 4 to 1. It scatters way more than red light. So there's red light being scattered as well, like kind of coming down, but there's way more blue light. So this person down here, they see the sunlight coming in, and when you look up, you see blue light, because what's being the atmosphere of our Earth is scattering the sunlight. And again, there's also other rays coming through here, but we can't see, like, infrared and stuff like this, right? We can only see, red through blue. So that's the color we have to, when I talk about colors here, that's why I'm only referring to those two. But it's sunlight, so it's all the wavelengths, right? But in terms of the ones we see, right, at first it starts to it starts to polarize or filter, however you want to think of the blue light. So if we're sitting closer to the sun, right, we're going to see the sky look blue. But someone who's sitting further ahead, what they're going to see is essentially by the time the light reaches them, see, all the blue light's going to be filtered out, and they're going to see red. And that's why you see, right, that would be like sunset time. And that's why, right, the sunlight has to travel longer through the atmosphere. So more light gets scattered, more of the blue light gets filtered out. So by the time it gets to you, it's red. And that's why you see it. So this is polarization by a surface, right? A surface would be our atmosphere. Okay. Just want to make sure you're not bored. All right. And now you can tell people why the sky is blue, right? Like, okay, now I actually know the sky is blue because it has to do with you can explain to your family about polarization and then the sunset and all that fun stuff. Okay. Um. Uh. Uh. So. Uh. Uh. uh Moving on. So this next part is kind of hard to talk about, but let's talk about what we can. So the next part is the lens stuff. But I think you all have a really good idea already for the lens stuff. You know that it's difficult. I mean, we can talk about the equation here. I mean, we can go through every picture. I can sit here and we can spend time going through every picture, but this is a picture that you're going to find in your book, in your slides, and hopefully you have this picture done already where like, I mean, me going through it one more time, I don't know how that's going to help you. I will totally do it if that's what you want me to do today. Okay, if you want me to draw a picture, I'll draw a picture. But the picture is, everyone understands what I'm saying, right? And maybe I'll draw one to refer to everything, but like, he wants you to know the difference between a converging lens and a diverging lens, just the picture between the two, right? So, but he gives you those pictures in the slides. Those pictures are found in your book. So it's better for you to just look at those pictures and memorize them. You should understand the math. And that, like I said, that's what we need to talk about. But those pictures, again, I could draw them, but anyway, let's get going here. Just keep that in mind, okay? That's kind of I might leave you to just go look at those pictures because I can't draw them like the like the book anyway. And also, oh yeah, I forgot I did this. I sent you all in an email. Remember that packet that I sent you all? Do you know what I'm referring to? That packet that literally went through everything that had to do with these lenses. So there's all that stuff. I mean, just I think you've all probably memorized that packet. So know that. I just want you to know, like, this is a review. Carl, why didn't you go through every picture? Because it's not gonna help you, right? It's better to look, that stuff. Look at the thing I sent you, because it's gonna help way more than some sloppy picture that I could send. Uh I can try to send it again, but I promise you it's gonna be in your, like, go to your Canvas inbox and just search my name and it should bring it up. It's gonna be from me. I sent it to everyone. Um, it was right before the second test. Did I might have put it in the announcements too. I can't remember what I did with that packet, I'll be honest with you. But I have it still on my computer. I can just send it out again with this video as well. But please, the my thing I want to stress is just look at that packet, okay? When it talks about these pictures and stuff, it's gonna be better. You'll be using your time a lot wiser, just looking at those on your own. Okay, so whether we're talking about a converging lens, a diverging lens, right? A convex mirror, concave mirror, it 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 doesn't matter, right? We're using this equation. In fact, we could even go as far, and it's the reason why, because it's just the application of this, is that this is and also what I was referring to at the beginning, is this is also the equation we use for vision, right? Why? Because our eyes are just this, thank you, Sarah. It was sent on March 28th. Thank you so much. So there's that email, but I'll try to send it out here. But so that's why, like, the equation for the eye didn't change, because the eye's just a lens. Like, it's nothing special than like what we were talking about here with the concave or convex. Now, you know, you know, your uh, your eyes shaped a certain way, but when we spoke about the the concave convex in terms of the eye, we were talking about the type of lens that you need to correct your vision, right? um uh so you know I guess, make sure you're not confused by that, I guess. But our eyes are a convex lens, right? Like the red, like our not that I'm a artist, but right. So just like this is a lens, right? and the sunlight comes through, and it's gonna do the things that it's gonna bend this uh, light in a certain way. See, this isn't gonna work, but imagine my eye ended there, and then so and that's still awful, but it's gonna do that, right, again, this is why I'm saying I can't be drawing these pictures, because I just, and then on this thing, but so I'll refer to the pictures, but let's make sure we understand the math. But for all these, whether it's the eye or just these basic lenses that we start with, the equation never changes. You're always using the same equation. Okay, and even when you get to because he at one point in this he was teaching about where you have two, we can have one lens, but then we could also have two lenses. You still use the same equation, it's just in that, right? So this would be, if we're dealing with one lens, you would only have to worry about this alone. But if you had two lenses, lined up next to each other, like a telescope or a microscope or something like this, right? You would want to and also remember, like, this is a generic way to write this. We'll talk about this in a second, because all these can have signs, right? You want to make sure that your uh, you're writing this the appropriate way, where each of these equations are going to describe a particular lens that the light is going through, right? But there's going to be an equation that connects them, and it connects them between the separation distance um, between the two lenses. And so that's this one. So this equation, and then you have the two for, right? This would be for lens one, and this would be for lens two. And sometimes, this could be a concave, this could be a convex, like, we could swap them. Sometimes it could be the same. I don't think he does that, but that's why I'm just labeling up, you should have, use the equation appropriately based off, if the second lens is a concave, then, treat that appropriately. If the second lens is a convex, treat it appropriately. Just like you would with the lens one. So this is the math in terms of just the lenses, right? It doesn't, even though we talked about a lot in there, it was a lot about him just wanting to make sure you understood the picture. Like, if you go through all his lecture slides, most of his clicker questions are just asking you, which way does the light bend? Which way does the light go? Which, again, we could do that in here, but you have the pictures that are done much nicer. And tomorrow, maybe tomorrow for SI, if you're still like confused about how to draw these rays, like, let's do it. I'll do it for you. But we have a lot of stuff to talk about. Most of that chapter was really just showing you, how the pictures are drawn, but the mathematics is pretty straightforward. Okay. The one thing you just have to remember is, and this is the stuff I want to ask you, and again, please, I'm going to smooth this over. What do we know about, like, P when it's real? Like, what should be its sign? Yeah. Okay. Good. And what about when it's, again, this is on a chart for you. I really don't need to even be doing this, but let's at least go through this part. So when P is positive, it's going to be real, and when it's negative, right, it's going to be virtual. And virtual, what is P? Oh, I forgot to ask you that. Like, what did it? Yeah. I mean, it's where the object is at. It's a way to think about it, but it's a distance. Like it's all this stuff are just distances. They're all just right. This is a distance. This is a distance. This is they're all just distances. And so it's it's the distance of object from lens. Okay, so if you have P can be virtual, like in the term in the case of like two lenses, because you're going to have this this is going to be formed right here, and then see this is Q1, but it's also P2 because it's going to be the object, right, for this lens, where then we end up with, right, this would be Q2. And so this one works. So in this case, like P is virtual because it's not a real object. Like the real object's over here, right? This would be P1. And so that's why like this Q1 acts like, right, it acts like a Q1 for this lens. Ooh. But then it acts like a object, a Q1. What am I saying? An image, an image for this lens, but an object for this one. I don't know what I was saying here. Okay. All right. So what is Q? I just told you. But good, image distance. Distance. I'm just gonna write it like that. That's not real nice. Good job. And then what do we know here about? Because it doesn't like that. If you notice the thing that I sent you in the email that I sent you, these the chart that you might have it memorized, but if you're looking at it, this is for everything, right? That chart's labeled mirrors and lenses, so it's not like, oh, like why aren't we talking about the mirrors here? Because this is the same for the mirrors. Okay, like none of this changed. This is mirrors, lens, whatever. This is how it works. Okay. If Q's positive, what do we know? Good. Real image. It just has to do with that real and virtual, right? Where like in this case, this is a real image, right? But this would be a virtual one, right? Because it's made off of the image already. It's not made off of the real object. If you want to know what the virtual means here. Cool. And then what about focal? I think this was the one that does have to do with lenses, but focal length's positive for what? I might need more space here. Converging lens or mirror, right? Good. And then negative for obviously diverging, right? Now, just remember, because there's so many situations we could go through, and we've done a lot of them in SI, and we can go through some tomorrow if you want. But remember, if you're trying to count, like in this case, if you know Q is virtual, right? But they're asking you to calculate it. Don't make Q negative. Don't start the equation this way. Be like, oh, Q is going to be virtual. Like you know already from your picture. You're like, okay, Q is going to be virtual. And so you're like, okay, I need to make Q. No. It's only negative like but you don't know the number of Q and they're asking you to solve for it. Keep it positive if you have to solve for it, and you should calculate a negative Q. So if Q is virtual and you calculate a positive Q, then you should go like, what the heck? This isn't right. Okay, so you should keep it positive if you're trying to count. Like, don't make any. This is what I'm trying to say. Let me say that better. I'm saying that really weird. If you're having to calculate for one of these values, P, Q, or F, then don't make the sign change, because the answer that you get should have the proper sign. And that's one way to check yourself. Because if you calculate it like you know the object's real and you calculate a negative P, you should be like, what the heck? This is, I use a real object here. P needs to be positive. So you can go back in your math and see what's wrong. Okay. Does that make sense what I'm saying? But if you're having to use it like it's a number, so like with the eyes, that's where I'm going here. Like with the eyes, we give you these numbers, right? Like, you know, like essentially Q here. Let's move forward here. Everyone good here? We're still talking about the same stuff. It's just, okay. So with the eye, right, we have the two situations, nearsighted, farsighted, right? And I think we know everyone's comfortable with the difference here, right? Are we good with that? Like the difference between like nearsighted and farsighted? Like, I mean, we know what they mean is what I'm asking. Okay. Nearsighted means you can see what? Far away, right? Farsighted means you can't see close up, right? So nearsighted. So we have two different things going on here, nearsighted versus farsighted, using this same equation. Like both of them start with this equation, but then it modifies a little bit based off of what's going on, right? So first of all, we're trying to talk about the thing that needs to be in your head, I guess conceptually, is this idea of far point and near point, right? So here we have this near point, right? Just to remind you. And so we have this near point and we have this far point, right? Where we're born with that's like healthy. Okay. So for our healthy far point is an infinite. Now this idea changes as we write the math. So just listen to everything here first. Okay. Listen to everything I'm saying here first. So you understand what I'm saying, because it can sound kind of complicated. We're born with this, like essentially we can see at an infinite distance. Like you can see stars, those are really far away. You can see the sun, right? You know how far the sun's away, farther than anything on earth away from you. And you can look up in the sky and see. So you can see far away. Okay. So you have this healthy far point, right? That is essentially infinite. But how do we interpret that in this equation? Your healthy far point is essentially going to be considered like the image distance, or the object distance, where essentially the object, right, for can be infinite, and we can see it clearly. We should be able to see it clearly. Why? Because our healthy far point is at that infinite point. So that's why we call P infinite, because that's where an object can be, and we should be able to see it naturally without any glasses or anything like this, right? But then we have this Q, that is what we actually call the actual far point. And this far point, right? It when you have an unhealthy eye, this number right here, right, is is uh isn't it infinite? Essentially, you have this new far point. You can only see to a certain point. You can no longer see at an infinite distance. You have this new far point. And this is only when you don't have 20/20 vision. Keep this in mind, okay? If you have 20/20 vision, then the far point's also equal to infinite for 20/20 vision. And then this equation is this. And you know what that is, right? Which it's trying to tell you you don't need glasses, essentially, right? But when our vision is unhealthy in some way, right, then we get this, our far point starts to change, and so that means that q in the equation starts to change. So this far point is going to be, you know, the point you can see clearly. So they're going to say, like, Tom can see, 50 meters away clearly, but can't see anything farther than that. What type of glass correction does he need? Well, that 50 meters is his what? They said that Tom can see at 50 meters clearly, but can't see any further than that.
That's
That
just
50, good. That's the new far point, right? Because otherwise the far point should be at infinity when he's healthy, right? So good. So that's the new, that's what we're trying to say. That's going to be, that's the unhealth, the where the far points change to. This guy, right, he should be able to see at infinite, but he can only see at 50 meters. Anything else is blurry. So good. So that's the point, and essentially that's the point where he can see clearly. So that's his far point. So, and that's how we give it to you in the questions, right? We say, like, this person can only see this far this clearly, or this person can only see this close this clearly, right? So we refer to the far point, or down here, Q is going to be the near point, where the healthy, like, if we have a healthy set of eyes, our healthy near point is 25, uh, uh, oops, I always write the meter one. The 25 centimeter, right? It's 0.25 meter, but 25 centimeters is like, this is healthy, right? So if you're seeing at if your eyes are healthy, then Q is also going to be 25 centimeters. But if it's not, they're going to say, hey, Sally can only see things at 100 centimeters and clearly, but nothing closer. What type of prescription does she need? What is that 100 meters? She can only see at 100 centimeters. Sorry, is what I said. She can only see at 100 centimeters closer, but can only see at 100 centimeters, but can't see any closer. That would be her what? Or near point, right? Okay, cool. Just making sure. It's hard to explain this stuff like quickly. I'm trying to kind of go through it quickly, but because I think you all have an understanding. So good. So essentially, these equations, right, end up a certain. So P is infinite, and here, right, we know a very large number on the bottom of something is going to equal a very, very small number. So essentially, we say that goes to zero. I mean, it might, but it comes so freaking close that it's practically zero. So this equation, because P is infinite, ends up being just 1 over Q, right? But so this is how we want to write it, right? But if we give you this number, like I said up here, we said, like, right, Tom could only see, I can't remember the number, but I said, Tom could only see, 200 meters clearly, but couldn't see anything farther than that. So I would give you, right, the 200 meters is what you'd want to put in here, but you have to remember that this now becomes negative, okay? Why does this become negative? And it's the same thing in the bottom too, but why does that become negative? So what does it refer, when we say virtual image? Yeah, you're right. It is, like Q is a virtual image, but what's it a virtual image? Like what, how, why is it a virtual? Because when our eyes see healthy, like if you're not, if you don't need glasses, right? Like you see healthy, does your eye create a real image or a virtual image on your retina? A real one, right? So Q would be positive in that case for like healthy eyes. So why is this Q negative? It's virtual Y. That's what I'm asking. What's making it virtual? That the images formed here are real for our eyes. Yeah, so the lenses form the virtual images for both. No matter whether it's farsighted or nearsighted, the lenses create a virtual image. And that's why Q, and they create a virtual image where? Where do they create a virtual image?
On the retina.
Um,
Well, no, actually, no, never mind, never mind.
so when we, so think of when you put on glasses, this is the situation now, where like this is your eye. Spelling there. This is your eye, and this would be like your glasses. So it works like a double lens now, right? So it forms it at your new, right? You have this point where you can see this far point and near point. So what your glasses do for you is that if you're nearsighted, it forms an image, a virtual image, right? Which, right, works as a virtual object for your eye now, when you would, which then projects a virtual image on the back of your eyeball because the object is virtual now. But it creates a virtual image at the point where you can see clearly. That's the whole, that's what glasses do. Because we can't, unless you get surgery on your eye, we can't change the shape of your eye. So your eye has this point where it can see clearly. There's nothing we can do about that. But what we can do is we can make glasses that'll take the image that you're trying to see and bring it to the point where you can see, where you just naturally, like, even though it's changed to some point, like for Tom, it's 200 meters. What glasses will do is they'll take any image that's super far away at some infinite point, and it'll create that image at his new far point. So we're at that 200 meters where he can see, and then he'll see that image, that virtual image at that 200 meters, and that's what his eyes see is the virtual image. Does that make sense what I'm saying? This is only for glasses, but it works for both farsighted and nearsighted that way. Does that make sense what I'm saying? Awesome. So again, you want to keep this equation the way it is, but if they give you a number, like I said, Sally can't see 50 centimeters is where she can see. She can't see any closer than 50 centimeters. So this, you'd have to make it negative on your own. So like, for example, like this equation would be 2.5 centimeters. Now it would be minus because I would have to know to make this negative because that number's negative. Why do I keep writing 0.25? I mean, I've been doing, anyway, you don't need to know that. And right, so it'd be like this type of situation, right? Does that make sense? Okay, so become right. We're not going to be given these numbers as negative, right? They're going to say Sally can see it's 50 centimeters. You're going to have to know by concept to make that thing negative. That's what I'm trying to. This part will never be in the question. The negative part. You're going to have to say, I know this is positive, but I know that this is the virtual image that's formed. And then that's why he wants you. Again, I can draw the pictures for you if you want me to, but I think it kind of, it's not something I can do, but it is something he wants you to know. So go in his slides. He shows you, he has two pictures, again, not drawn by hand because that wouldn't give you a really good picture, but he has two pictures drawn with computer. And I think your book has the same pictures. And actually, I think I also sent in the packet I sent you, or maybe not, maybe I didn't have that. But anyway, make sure you know the picture. Make sure you know how to draw that virtual image at that particular point. Again, I can do it for you if you want to, but it's in your slides. It's just copying that picture. All right. Is that okay to do, or did you want me to draw those pictures as well? Like he wants you to be able to draw like how the vision's corrected for farsightedness and nearsightedness with a ray diagram. That's what I'm saying. Is it cool? Just like I asked you with the lenses, to just look at the picture. Okay. Because it's good. I don't mind explaining them to you. And if you want to send me an email saying, Carl, okay, I'm looking at this picture and I've been staring at it for 2 hours and I don't understand what the heck it means, please send me an email. I'll tell you what it means. Okay. I don't want that. And I have no problem explaining these things to you. It's just these pictures or, anyway. Okay. And then also know, he talks, I'm not talking about them, but, he goes into a little bit about magnification and stuff like this. So make sure you understand that stuff. Okay. But right. Cause he talks about like magnifying lenses and stuff. I mean, there's all kinds of stuff we can do that relates to this equation. Okay. That's what all this stuff up until the interference diffraction, all that is dealing with is this equation. Okay. But then, and that's what we're switching over to now. Once we hit the interference and diffraction, we've changed from geometrical physics or a geometrical way to look at light to a physical way to look at light, which is in terms of not just how the angles are working and things like this, but we're looking at it in terms of like the wave and how the wave actually behaves. So because of that, all these these equations right here, right, we don't really come back to them in those because we're trying to discuss something a little bit different. These were very, very specific equations just for the geometrical way to look at light. So interference and diffraction. Again, I think why we got a little confused here. First of all, because I mean, man, I remember the first time I was given all this stuff in physics. Like it was intimidating. I mean, I'm a capable person, but like just getting, starting to talk about this stuff, moving into this stuff, you're talking about these waves and things and you, in your brain, it just, you go, man, this is tricky stuff. This looks like, pretty complicated things that we're talking about here, but it's really, really not. It's really straightforward. And actually, I think I explained to most of you, most professors who talk, who talk about interference and diffraction, they spend like maybe 30 minutes on it because it's just a very small idea to understand kind of in the grand scheme of things, how waves are interacting, just how waves interact. That's really the idea here, and not just any type of waves, but how light waves interact. But keep in mind that right after this chapter, and that's what we'll get to, is that we said that most fundamental matter behaves like a wave and particles. So photons, everything we talk about here, and talk about a photon, the way it like propagates and the way that it bends, right? Moves through certain slits in a certain way and bends. The slit makes that bend and cause certain interferences. Electrons work the same exact way. Okay, all fundamental matter that can be both described as a wave and a particle, they work the same way as we're describing this light here. So keep that in mind. Okay, so this chapter started off with just like constructive and deconstructive interference, just to make sure that you understood that idea, because that's essentially what this whole chapter is trying to talk about. We're trying to talk about two things. One, the interference, right? So we're talking about interference, which is this constructive, deconstructive idea, okay? And then diffraction, which is how the light bends, okay? And so what's going on here? So the constructive and deconstructive interference, right? When we talk about that, this is talking about waves just interfering based off their amplitudes, right? So if I have what the heck is going on here? If I have a wave, right, like this, and then another wave, like this, right? They're gonna interfere in a particular way based off like how they're lined up, right? If they were perfectly, like if the green line was like this with the red line, then that would be total constructive interference, right? It would, both those amplitudes would directly, right, add to give a much larger, and not that's always what happens with constructive interference, is the amplitudes sum together to give a larger amplitude, where deconstructive interference is where the amplitudes sum together to give a smaller amplitude, right? So here we get small amplitude and large amplitude, based off of how they're interfering, right? So they constructively interfere, they're going to add together to give way to a wavelength that's going to be the two amplitudes added together. Deconstructive is going to give way to a wavelength that's going to be related to how the amplitudes are subtracted from each other to give way to a smaller wave. Does that make sense what I'm saying? And then like completely out of phase, right, would be like that yellow one right there. I know there's a lot of waves there, but like the green and red one are kind of interfering and constructively and deconstructively, kind of like depend on what's going on, right? But the yellow and the red are total, like they're interfering totally. So the result of the red and yellow, red is gonna actually let's sort of have this frame like this. So if I have this, that's like total deconstructive. So these two, right, are gonna lead to They should be. I try to make them the exact amplitudes, but they don't look exact, but they should be exact. I kind of messed this one up over here. But the resulting wave, because they're totally deconstructively interfering, is going to be that. There's not going to be anything because the amplitudes are subtracting. This would be like A1. This would be A2, right? They're subtracting from each other. There's nothing left. Okay, versus whoa, right? If they're together, then it's going to be these on top of, like, essentially added together. So the amplitude for the resulting wave should actually be larger. And how much larger? Literally, like you can measure that with your fingers and then put it on top of the blue wave. And that's literally how you can actually get the actual size of this resulting wave. Just like, use your fingers, put your fingers like at that width and then move that up here on top, like start that right here. I can't do it because the wave's at the top, but I think you understand what I'm saying. Like you can actually get the size if you wanted to just by doing that. But you can this would be A1, this would be A2, right? This is just adding them together. And here you'd have some, like, this would be A total. Some left, them added together. So that's total constructive interference. Okay, so that's if all, like, the total amplitudes of both interfere. But you can have something in between where there's like a little bit of constructive, a little bit of deconstructive, and that is definitely a little bit hard. What is happening there? That is definitely a little bit harder to draw, but so like right here it'd be constructive, right? And then here we'd see this would be deconstructive, right? And then here would be a little constructive. And then anyway, you're not going to have to do this, but that's the idea, is that some that are a little bit off of each other, they're not going to totally go through constructive. You don't need to do that. I don't know why I was going to, but they won't totally constructive interfere, totally deconstructive interfere. They'll do something in between. Okay, everyone good with that? Like that's the main idea. Okay, and so that's what we're trying to talk about with the constructive and just the interference. So when we were talking about that interference, we were just and showing you those patterns for like the double slit. The double slit, we weren't trying to add in any diffraction, which means we weren't trying to, and I haven't described that yet, trying to describe how these waves are going to interact because of their path lengths. Their path lengths are going to end up being different because if some of them bend, right? If all of them were moving straight like this, then the distance from the slit to the screen for all of them would be the same. And then it would just be based off of, the waves, like how they're, and again, I'm not good at doing this, but this is essentially how you do it. But how the waves like are, and please, that's not done very well. I was just trying to draw something, right? And and this would be kind of just looking at like how the waves are constructively, interfering and deconstructively interfering at a certain point. But then what happens is that because the light also bends, and we'll talk about that here in a second, that means that this light, right? This takes the light traveling from this point here. Let me draw that a little bit better. Better color as well. So the light traveling from here to this point, and the light, so here's one source from one slit, here's one source from another slit, and then another bit of light, both traveling to that same point, right? Just because of their path length difference, they're going to interfere. But then also because of the way the waves are interacting due to constructive and deconstructive interference. They're going to also interfere because of that as well. Okay, so what we were doing at the beginning was with double slits, just trying to talk about how they interfere in terms of just their waves interacting constructively and deconstructively. Okay, I can't draw this very well, but you know, you want to be able to draw this pitch. See, I can't do it anyway. But that's what we're trying to. I'm better when I do it like this. Trying to draw it like how your book does, but I can't. Like, this is the only way for some reason I can do it. But we see that like where they're cross, right? Where they cross, what do we when they cross, what do we know about when they cross? What do we know about and again, this isn't perfect, but yeah, we're gonna have what type, I guess, yeah, you're saying slits of light. Why do we have slits of light? Because good constructive interference, right? And so that's right off those pictures, like that's what he wants you. And again, this picture is not drawn well, but I'm just trying to show you something here. Right, like that's everywhere. So like here, right, and we see a little right here again, this isn't perfect, but you know, roughly where they're crossing here, right? And then we can see here, right, that we have this, and then we have this, and then we have this, and we have this, and we have this, right? So and that's just based off like construct that has nothing to do with the way it's, I know it looks like the way it's bending, but I'm just trying to show you the rays and how they're lining up. I'm not trying to show like this is their path length difference. I'm just trying to show you. Does that make sense what I'm saying? Like this is, I'm just trying to say like that goes there, that goes there, that goes there. Again, please look at your book, has the best pictures, and so does your slide, because he wants you to kind of understand this, like where they're crossing, and then where they're like this, they're at a phase of each other. So that's where you always have like deconstruct. That's why like right here, right, we have no light because there's deconstructive interference. And this is just because of the way the waves are acting, because of the way, right, as right, there's these two slits here. There's going to be this one bit of light. This light is one giant ray before it moves through these slits, and it moves through these slits, and the slits separate the light into two separate waves, and then those two separate waves start to interact, and they're going to interact constructively and deconstructively, and this is the situation you get. So does everyone understand that? Okay, and he gave you just direct equations. You should just know, like, directly, he gave you equations here. And this is for constructive. So this is just trying to describe all the peaks. Okay, this equation. And then deconstructive, which looks almost identical, which is just trying to describe the troughs, right? Okay, so this is deconstructive. And this is just based off of, this has nothing, this just has to do with, like, you know, the distance that it has to move to the screen from the slits, and how that ends up setting up. I kind of wrote those in not a good place. Let me rewrite them down here. So we have E sine theta so right, so we have some distance, and that distance to the screen what variable do we use for that? D, right? And what variable do we use from the distance from peak to peak? Or what we say fringe to fringe? Because you can, this is also true from like one dark fringe to another. This is the same variable. It's just really fringe to fringe. What variable do we use for that? X, good. So fringe to fringe, whether it's dark fringe to dark fringe or bright fringe to bright fringe, okay, that's X. So the other way to write these equations, right, which would be dx, so sine theta for small angle approximation, and don't worry, you don't need to know the y's here, but know that when we use small angle approximation, sine theta ends up being equal to x over d. We can write this equation in terms of, right, and then that little d is what? What is the little d in that equation? So that's the distance between slits. That little d. Okay, so big D, have it written on the right, is the distance from the slits to the screen. X is the distance, it's on the top right, and it's the distance between either bright fringe to bright fringe or dark fringe to dark fringe. Doesn't matter, it means the same. Right? And little d, which is sitting right above the slits, right, is the distance between the two slits. And it's measured from center of slit to center of slit. I don't know if he even asked you about that. Right, so I'm just marking out these equations. So these are the equations for constructive interference just based off of, the distance those waves have to travel from the slits to the screen. They're going to constructively and deconstructively interfere just because of how the waves are separating up here. But we also know, and it's true there, this is, again, even though we're just using this about interference, diffraction is also occurring here. And the reason why actually that diffraction is occurring here is because if this was just an interference pattern, the intensity would actually be like the pattern you would see would actually look like this. Like it wouldn't, there would be that, let me draw that better. You'd have that bright, or I shouldn't call it bright middle fringe because it wouldn't be that anymore. You'd have that middle fringe, but then the one right next to it that's lower, it would actually be the same intensity, and the one right next to it, because you would just have these places where they're constructively or deconstructively interfering, just based off of the difference in their wavelength pattern. Okay, but because there's also diffraction here, the light is bending. This is for a double slit here. Because the light's also bending, we see the intensity pattern, right, ends up looking like what we just made, which is, it has this bright fringe and then the next one, and it gradually, right, gets less and less as you move. Okay, because this is what this pattern looks like with interference and diffraction. But he just wants you to know, because he wants you to be able to draw this graph. Like you should, just in general, this is the graph that you should have for the intensity graph for a double slit, because he wants you to know, like, what's the intensity graph for a double slit? It's this one, where, see how it gradually decreases here? How's that look different for a single slit? Well, this is, and the reason why there's a difference here is because it takes, a single slit is using a lot more diffraction than the double slit is. You'll see what I mean here in a second. But what happens in terms of the intensity graph, which you need to know for this, for the so this is double single slit, you end up with this really bright fringe in the center. And then what happens is like these off to the side are really tiny, really tiny. And the reason for this, like I said, this is single slit down here, is because it takes, like, there's a lot more of interference due to diffraction than there is for the double slit. They're both of them are taking advantage of diffraction and interference, but the single slit causes a lot more diffraction because of the way we describe what's going on in the slit. This is what I mean. So for a double slit, right, if we were to look at a particular point, say like right here on the screen, we would have, right, a particular point on the screen due to both of those slits. What we would see is that, yeah, we know because of constructive and deconstructive interference, because these waves are going to arrive at this point, right, at a you know, either at a max amplitude or a minimum amplitude, right? Some of them are going to, you know, get there, and some of them are going to be peaked, right? Some of them are going to get there, and some of them are going to be troughed, right? Just because of the way that they're moving to get there. But then there's also, because of those two slits, right, there's going to be a path length difference. And he wants you to be able to draw this as well. And the path length difference, let me draw that better. The path length difference, is where this is 90 degrees right here. So this right here is going to be the path length difference between those two rays. So there's going to be some interference just because of the way the waves are arriving there in terms of their amplitude, but there's also going to be some difference in the waves arriving there because of their path length difference. But in terms of two slits, this is the only path length difference that those two rays that are emerging from here, or those two bits of light, are gonna deal with. Okay, why is that such a big deal? Because for single slit, where we have just one slit here, let me draw that better. Essentially, each point here works as an individual slit. So there's going to be way more, right? So instead of having a path like arriving at this point, right here, the wave arriving at this point, instead of the diffraction pattern ending up being over here based off of these 2 points, it's actually going to be based off of what, like all of those, right? And as we see, this is what he was trying to show you in the slides, is that all these things, right, because of this, every single one of these points right here end up being a path length difference from themselves. So because each point works as a point of light for a new ray that's being emitted, so essentially all these are new, instead of just having these two slits right here with just the two rays coming out, right, and interfering this way, this one has like a gazillion coming out. Like at one point, it's like almost hard to like, and if you look at his picture, I can't even draw this. I mean, it's going to end up being really messy, but he gives you a picture on the worksheet that ends up, you know, doing something like this. I'm not doing it justice here, but what I'm trying to show you is that for the single slit, we're trying to explain diffraction in terms of, or interference in terms of diffraction, because this light, right, it's going to take, because of the way that it bends at this particular point over here, it's going to take it, they're all going to have different paths once they reach over here. And because they're all going to have different paths, if one, what we found out, I guess what I should say, what we found out, the concept that we found out here is that each one of these paths is equal to 1/2 wavelength. So each one of these path length differences for each individual slit within this single slit is going to be 1/2 wavelength difference from each other. And it's because of that why we see so much more deconstructive interference, because the waves are arriving at this point out of phase with one another. Essentially, they're all deconstructively interfering with each other at some certain angle. The only place that they're really not going through a lot of deconstructive interference is right down the center, right? You know, like right, like where that really super bright fringe right down the center. This is the only place where all these things are really going through the same path length, right? They're traveling the same distance to that middle point. But any point off the side of that bright point, so this really bright point, they're all traveling the same distance to get there. So they end up constructively interfering because they take the same distance to get there. But then over here, off to the side, as you can see, since they're all a half path length off from each other, they there's barely any constructive interference over here. And so if you look at his worksheet that he has you do for this, you end up getting this pattern where they all deconstructively interfere. And that's what he's trying to talk about. That's what he's trying to get you to see, is like they all have a half path length, half wavelength path difference from one another. There's 4 rays there. And so because they're all half path length, a half wavelength path difference of one another, they're all going to deconstructively interfere with each other. So there's not going to be any resulting light from those 4 waves that are going to reach the screen. And that's essentially what he's trying to describe. That worksheet's trying to describe this particular situation right here. So with all that being said, at the end of the day, for diffraction, we have an equation, but the equation that we have is very specific to only the dark fringes. This equate, because of what we just talked about, there's way more deconstructive interference than constructive interference. So diffraction, right? The equation for the diffraction is trying to describe those points where there's dark fringes, where there's the deconstructive interference due to the path length difference. Okay, and so this equation right here, again, it can be written two ways, but it can only be used. Please keep that in mind, that it can only be used for deconstructive interference. So you can't use it to solve for like the bright fringes, is what I'm trying to say. Okay. So, and this can also be written, sine theta can also be written in terms of x over d. So, or the theta can. Sorry. So that's another way to write this equation. Again, this m, though, I guess what's appropriate, or what you need to know based off what I'm trying to tell you, this is only for deconstructive interference, is that this m can't be equal to 0. And why is that? How come this, if this is only for deconstructive, good. So these peaks, they relate to something, right? We haven't put that on here. but these peaks relate to the M's, right? So that middle peak, and it doesn't matter if it's single slit or double slit, that middle peak is always going to be where M is equal to 0. And you can also see that these equations are essentially quantized. These M's quantize these equations. They're just based off like particular integers. That's also something to kind of pay attention to. But then what we see is that here, right, M is equal to +1. And for this, like a trough can have any integer value and right other than 0, where peaks can have integer values of 0 or 1, 2, 3, 4, right? So troughs can only have integer values of 1, 2, 3, 4. They can't have use 0 whatsoever, because that M equals 0 is dedicated just to that one middle bright spot. All right. And this is also like what the M's mean in here, in case you didn't know what the heck the M's were referring to. They're referring to the different, troughs and peaks, right? And this negative and positive, it just has to do, there's an axis point right here, right? Where this is positive X on this side and this is negative X on this side. So these end up being negative because this is negative and this is positive X. These are positive, like that's why. And it's not the direction they're pointing. You want to think more of like just graphically, this line right here separates like positive and negative from each side. So that's where they're getting their positive and negative signs, but they don't mean anything different. Like M-1 and M+1 for a bright fringe is describing the same thing. They're just describing that fringe on one side versus the other. That's all that means. Does that make sense what I'm saying? Okay. So again, what's going on here? Interference and diffraction. Double slit is trying to just describe how the waves are interacting based off of, constructive and deconstructive interference, which is just how their amplitudes arrive, right? Based off how their amplitudes arrive at the screen. Where interference is trying to describe how they're going to interact constructively or deconstructively based off the path difference that they have to take to the screen. Does that make sense? You see the difference between the two now, what we're trying to explain? But remember, at the end of the day, they both happen at the same time. Interference and diffraction happen at the same time for like whether it's double slit or single slit. We're just showing you the examples separately, but you should know that those patterns look the way they do because you're having interference and diffraction for both. Does that make sense what I'm saying? Everyone good with that? Okay. Because I know this is where the most confusion is, and I don't want you to be confused here, because that's all we were trying to say. And I know single slits, double slit, they can get very confusing, and you're hearing all these words, but that's all that was going on. Okay, so after we talked about this, right, we talked about just thin films, right? And the thin films were just really trying to be based off of, even though it didn't seem like the double slit and single slit, the thin films were just trying to talk about interference still. And it was trying to talk about interference based off both of these things at the same time. Okay, so like when we have a thin film, I gotta recycle some of this. When we have a thin film, right, essentially it's that film is going to be something within here. Like this could be air, this could be, I don't know, soap or something, this could be something else, right? Or it could be air again. I don't know, it doesn't matter, right? but or let's say that it's water or something. So, right, and we want to know like how these waves are gonna interfere, both based off of like how they're being reflected off the boundary, and then due to the path length difference that they're also um, taking to one another. That's essentially what's occurring and why we end up having um, um, these patterns over here that we have to end up looking at, where things are they can flip their wavelength or change their phase by pi, or they can stay in phase. Their phase doesn't change at all, based off what's going on here. So what do we remember here? When a light goes from a soft boundary to a hard boundary, what is the reflected ray going to do? So here we have soft, and it's soft only because the next boundary is larger, right? The one could be a hard boundary if there was a boundary before it that was less than one, even though that's not possible. But what happens? What type of when we reflect off of a hard boundary, do we get a phase? Is there a phase shift in the wave, or is the reflected ray, does it stay in phase with the incident ray? Good. So any hard boundary, when you go from a larger index of refraction to a harder index of refraction, the reflected ray is always going to go through a pi shift. Okay, always. What about when we go from let's change this. It's still going to be a hard boundary, right? So what happens when we go again? So now we're going from 120, but now the next one is 150. So 120 was a hard boundary to the one, or 1.20 was a boundary to the one above it, right? But the 1.5 is going to be a hard boundary to the 1.2. So that's also going to go through what? A phase shift, right? Because it's still going from, even though this was harder than this one, if you're going to another harder boundary, you can still have another phase shift, right? And then, right, there's always, like we were talking about at the beginning about the transmission, right? So this is the reflection transmission stuff coming back again. And then here, right, this hits a soft boundary. So what does that mean? What's going to happen there? Is there going to be a phase shift when we hit a soft boundary? Is there any kind of pi shift to the reflected ray when we go through, when we hit a soft boundary? Yeah. So, right, and you can, there's a lot of, we could keep going here, but the thing to pay attention to, right? And if we had another ray right here that was also 0, let's say didn't go through any phase shift, right? Then we would see that if these match here, so if it's 0, 0, there's, we have two rays that arrive that are reflected back that don't go through any type of pi shift, or we have two reflected rays that both go through a pi shift. Both of those are going to be constructive interference, right? That's constructive. That's constructive, right? Because they match. They're both still oscillating together, even though they both went through a pi shift. They went through the same pi shift, so they're oscillating together. But these two didn't go through a pi shift, so they were oscillating together before, and they're oscillating together after they're reflected. But if they're opposite of each other, like pi and 0, then we know that that is deconstructive, right? So you want to be able, like, we did a lot here. And one of the things he wants you to be able to do here is just, be able to draw this picture. That's one of the main things, be able to look at boundaries, hard or soft, like we did over here, and then be able to decide, hey, what's going to happen to the reflected ray, and then be able to say, okay, that reflected ray, are those two reflected rays going to go through constructive interference or deconstructive interference? Okay, so this is one thing alone that he wants you to know. But then there's also particular equations that you can use to solve for, like, he could ask you, like, what colors of light are you going to see? What, based off the type of interference that you're getting here, what are you, if you are going to see a color, what color would you see? Or what colors are going to be absent, or anything like this. He could ask you these different types of questions. So that kind of is, I think I gave it all to you. That kind of takes, it's kind of hard to explain that part without working through a problem and saying, okay, because of this, and based off what's being said in the problem, like, this is the way that you need to solve this question. And that alone could take, working through one of those things could take 15-20 minutes. And so I don't want to spend this review, working through something that takes that long, when there's potentially only going to be one question on the test about it. Okay, so if he does ask you about this, it would only be, one question related to this stuff, but it's probably going to be more about these pictures, because the worksheet that he gave you for this section is just really having you do this. He doesn't have you really play with any of the equations. But know that, there are two equations that go here. One of them is this one, and the other one is this one. And so, and this is for constructive and deconstructive. Yeah. Lost my slide. Where did it go? Okay. So, I mean, that's gonna, but to use these equations, and that's what I was talking about, it's kind of a different story. If those of you who came to SI when we worked through these equations, you know what I'm talking about, because we had to, essentially what I do is I have to give you a chart, and then I have to show you how to use the chart. The chart makes things a lot easier, but I have to show you how to use it. And so tomorrow, if you want to know how to do that, tomorrow I can go through that. I don't mind spending some time for the review tomorrow, because tomorrow for the review, I know I said it's only going to go an hour and a half, but I'll go as long as if we end up staying there till 10 or whatever, I don't care. But I don't mind explaining that tomorrow to you and solving through a problem and showing you how to use that chart that helps you solve problems using this idea. But the picture, you can't solve those problems without the picture, and the picture is what he's wanting you to do on the worksheet. So it's really important that you're able to do this picture that's in front of you, solving the problem that's associated with this question, which he only gave you one clicker question about it. It's not like he gave you a ton. We can talk about tomorrow. Does that work? Is everyone okay with that? Okay. I just don't want to leave you hanging, but that's kind of a thing. And like you said, he asked you one clicker question about it. It took a long time to explain, but all for just one question, and again, he has 15 questions from this later stuff that he hasn't tested you on to ask you questions about. So, and using his slides as a guide, he really doesn't ask you many of those questions. So on to relativity. Okay. So here, I don't think we need to get into. I mean, he went through a lot of things to explain the idea of relativity to you. I don't know if we have to go into those things very much. If we do, let me know. But really, I think when we start to talk about the equation kind of like sets everything into play. Like, we could talk about the concepts all day, but then, when we talk about the equation really allows us, like, it gives us a good idea of what's going on. Where the concepts, you could talk about the concepts and be like, wait a minute, is the photon moving at the speed of light? Or I thought, how's the environment moving at the speed of light? I thought the photon, right? We could talk about the concepts and they can get very twisted in that way. But the equation kind of like keeps things untwisted for us as we start to describe things. So first of all, the thing that needs to be in your head when we talk about special relativity is what? I've asked you this before, but the minute that special relativity is even said, what are we trying to talk about? There's only one thing. There's only one thing. What is our theme here? What are we trying to? When we bring up that word, it means, oh, they're only talking about this. This doesn't apply to anything else. Let me say special relativity is being applied here. Relativistic effects occur. Like, all those things don't happen every day. What has to be occurring in order for special relativity, the things that we've learned about special relativity to even occur. Oh, yes. Moving near the speed of light. Yes. So that's the point of special relativity. Okay. Every time we bring up that word, that's the first thing that should pop in your head. We're trying to describe motion when we're moving at the speed of light, or an object. It doesn't have to be you. It could be an object moving at the speed of light. Okay. It's not trying to describe anything else. When you don't move at the speed of light, things essentially become Newtonian and there aren't many relativistic effects. I mean, yes, if you're sitting on the couch with your friends, and then you get up from that couch and start to walk around your house, and your friends stay sitting there on your couch, yes, you are experiencing time dilation. You are. Like, your time's ticking different for you than your friends because you're up moving around, right? And your friends are sitting still because you're moving closer to the speed of light than they are. But that is like to measure that it's so tiny. It's very, 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 very tiny. Okay. And because what makes that measurement tiny? The Lorentz factor. Okay. And the Lorentz factor is really trying to describe when those relativistic effects kick in. And there's a lot of things going on in the Lorentz factor, but the thing that's the most important is that it's really just looking at the difference in speed for that. Like, this is the object speed. And it's really just looking at that Lorentz factor, right? Even though, there's fraction stuff like this, it doesn't, right? The only real variables in there are the object speed and the speed of light. Okay. And so when you have a very small, like, you're going to get a number there, you're going to put, your very small velocity in there, with a very small, large number at the bottom of your very small velocity, that means that the number is going to be very small. So when you have, and he was trying to show you this with a chart, or a graph, it's in your slides. But the Lorentz factor, when it's really, really tiny, when you have a small Lorentz factor, which, like, objects moving at normal speeds have very small Lorentz factors, that means that you're not, there's, the smaller the Lorentz factor, the less likely you're going to have relativistic effects, time dilation, length contraction. But the larger and larger your gamma gets, the larger and larger your Lorentz factor gets, and that's going to get larger and larger because this ratio gets larger, because your speed gets larger and larger. So the closer and closer you get to the speed of light, the larger and larger your Lorentz factor gets. And that's the thing determining if there's going to be some sort of relativistic effects going on. What are those effects? Time dilation and length contraction. Okay, so they won't occur really because of this equation, because this has to be very large. They won't occur until you're moving very fast. But once your Lorentz factor is large enough, you know, like when you're near the speed of light, your Lorentz factor is huge. It like goes, it exponentially grows at a certain point. It just like gets very, very large very quickly. And those are the points where you have relativistic effects. Okay, so relativity, what is it trying to describe? Motion moving at the speed of light. How do we know when special things are going to occur at the speed of light? Because our Lorentz factor is telling us that, you know, when your speed, the ratio of your speed to the speed of light becomes measurable, something, you know, something that, you know, large enough to measure, that these effects that we're about to talk about are measurable. Time dilation isn't just this small little thing like your friend sitting on the couch and you moving around, which is essentially no value at all. It ends up being this thing where, you know, you're moving at the speed of light. You could experience 5 years and your family could experience 100 years, right? And you both feel like you went, right? Anyway, that's where we're trying to get. So does that make sense here about the Lorentz factor? How it determines, that's the whole point of the Lorentz factor, is it determines relativist effect when they're going to occur. Okay, so then we have these two equations that are describing the things that are going to occur at the speed of light. Okay, one of them's time dilation, one of them's length contraction. So who does time dilation occur for? Who's the person that experiences time dilation? Oops.
Observer.
That's good, but remember, like the reason why I started off this discussion this way about moving at the speed of light is because that's the way we should be thinking. If you're saying the observer, anybody could be the observer. You see what I'm saying? And that's one of the things we were trying to show you with this chapter, is like the observer.
So the observer who's not moving at the speed of light.
Yes, the person, the one that isn't moving at the speed of light. Exactly. Good. And when you talk about frame of reference, trust me, we can talk about all these things, but I think they complicate words because it's like, I've never used that word of frame of reference before, and now I'm trying to use it in things and it can get a little complicated. I mean, we could have been, trust me, frames of reference comes from Newton's first law. So we could have been talking about frames of reference for, you know, since physics 1. But instead of thinking that way, to say it another way, because this is what should be in your head. I mean, this is the way it works every time, despite using those words of observer or all those things, is that what should be in your head, the science that should be in your head, is that time dilation only occurs for the person not moving at the speed of light. Or I shouldn't say person, I should say object. I mean, that's the way it works. I mean, we could sit here and talk about observer and things all day long, but it makes this discussion really complicated. And then we're like, wait a minute, who's the observer? Like, trust me, I get like that sometimes still when we use those words. It's like, just talk this way because this is the way it works. Like, I understand, you know, like they want to teach it to us that way. But I mean, you know, at the end of the day, there's something we need to know. There's something we know. Let's talk that way, right? Like time dilation never occurs for the person moving at the speed of light. To them, they're experiencing what we call proper time. And to them, you know, yeah, they're moving at the speed of light, but they don't really know that. They look down at their watch They look at the spaceship around them inside. They're inside their spaceship. Nothing's moving. It's like when you're inside your car and you're moving 50 miles an hour down the highway. Well, if you're looking at your window, right? Yeah, it looks like everything's zooming past you really fast. But if you kind of like lean back and look at your door with the perspective of what's going on outside, it looks like everything inside the car is staying still, right? Your door's not moving. It looks like the outside is moving, right? You're sitting in your car, you're looking around, you're like, we're all sitting still. Nobody's moving. Like if you threw a ball up and down, it would work the same way as if you were sitting still. It wouldn't like, you everything that's happening in the car occurs as if you're sitting still, right? And that's what we're saying is that this person who's moving, even though they're moving at the speed of light, to them inside their spaceship, everything's everything's sitting still. Time is ticking off normal. They look down at their watch and the seconds are ticking off like normal, right? But if the person in the spaceship were to look through a telescope and look at the person's watch on Earth, the person's watch on Earth would be going so fast. They'd be like, whoa, 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 right? And if the person on the spaceship were to beam to Earth really quick, say, wait a minute, I got to check this out, and beam to Earth real quick, they'd get to Earth, and that person's watch would be ticking normally. And the guy would be looking at his watch and be like, okay, well, our watches match right now. They're both ticking off seconds the same. I'm going to go back to my spaceship because I swear I saw something different. So the guy beams back to his spaceship, right? Looks through the telescope again and looks at his friend's watch, and his friend's watch is ticking slow again. He's like, what the heck is going on? Nothing. I'm sorry, ticking fast. Nothing's going on. That's what at the speed of light, that's what starts to happen. It has to do with your difference in speed. So the faster and faster you go, the less you experience time, right? Where that person sitting still, they experience a lot more time than you do. All right. So they're even if they're moving around in their car, relative to you, moving 60 miles per hour versus moving at the speed of light, that's like sitting still. So all that motion, it doesn't matter, and time starts to tick for you a lot faster than the person at the speed of light, because this person at the speed of light is not experiencing time. Really, if they were to move at the speed of light, they wouldn't experience time at all. It would be non-existent to them. Okay, but the closer and closer you get, the less and less you experience time. So, and everyone who's not moving at the speed of light compared to you, their time is ticking normally. So it's going to be like their watches are ticking faster than yours because your watch isn't ticking at all. Okay, and that's time dilation, and it only happens for the person moving at the speed of light. The proper time, which we say it's the time being recorded by the person sitting still, that is the person moving at the speed of light. The person moving at the speed of light, their watch is sitting still. Okay, the person at Earth, when they look at the person's watch, it looks like it's moving, but for the person on the spaceship, their watch isn't moving. And you have to keep in mind, the only person who has a watch here is the person moving at the speed of light. The person on Earth doesn't have a watch, just the person moving at the speed of light. And they're just recording the time. The seconds tick by like normal. And so this person, the seconds start to tick faster, faster. Does that make sense? That's what needs to be in your head. And then this gamma we already talked about. So again, there's no equations on the equation sheet for relativity? Are there some for quantum mechanics? Does it like end at waves or something? What? Send him an email tomorrow. He's gonna give them to you. He has to. He wouldn't expect you to memorize them, but you should have them already to study with. That's not good. So please send him an email. I mean, send it tonight if you want to. He'll answer you first thing in the morning. That way you can wake up to the answer. But please send him an email and say, Dr. Ngana, you should have those equations, okay? You shouldn't have to memorize any equations. That's not required for him. Oh, it might be on the so Jenna's saying a modern equation sheet, and that sounds like it might be on there because all the stuff we're talking, all this stuff, relativity, quantum mechanics, that's all modern physics. That's what we call it. Oh, okay. So Jenna found it. She said that there's a. I'm assuming it's where the other equation sheet is. It's just labeled modern. So I think it's where. Does that make sense, Mabel? Because Mabel's asking where it is. In files on Canvas. Thank you, Diana. So, okay, cool. So, yeah, absolutely not have to memorize equations here. No. Okay. And then the length contraction, right, which is just the other equation that we talked about in this. If you can't find it, let us know. In this chapter, which this one could be a little bit more complicated because like with time dilation, right? And it's true here. Like it's only true for one thing. Like only one thing experiences length contraction. But we bring in the idea of relativity a lot more into this idea where, you know, we're saying, well, it's relative to you know who you're talking about, right? Like I can be the you know the person outside observing something move at the speed of light, or I could be the object moving at the speed of light and imagine that everything around me, like I'm sitting still and everything around me is moving at the speed of light, right? So I could stand out here and I could watch like a particle, right, which has like this much length to it, move at the speed of light through this tube. But as I watch that particle move through this tube, it would only look this long. It would have some sort of contracted length compared to its proper length, the length that I would measure if it was just sitting still, right? So that's what this person would see. They would see this. Okay, the particle, because it's moving at the speed of light, would look shorter. It would have some sort of length contraction to the person not moving at the speed of light. But to the particle, it looks like the pipe. It's now I didn't draw it in there, but the particle's like in here, right? So to it, it looks like the particle's like, I'm not moving at the speed of light. And it literally physically works this way. This isn't like, it's not imagining anything. Like literally to the particle, it looks like the environment's moving, not it. It doesn't know that it's moving at the speed of light. Like literally doesn't know. Why? Because it's experiencing the environment move around it, not it move. And so the particle, even though it's moving at the speed of light, moving through this tube at this certain length, the particle is only going to experience. So this length right here would be the proper length of the tube, but the particle would experience the tube since the tube is moving at the speed of light to the particle. The particle would experience the tube as only, you know, like a lot shorter than what it actually is. It would experience the tube at a contracted length. The particle wouldn't contract, the tube would contract. So who experiences the contracted length? Or whose length contracts? Let me say it like this, because I want to make sure I say it in the right way so it's not confusing. What object's length contracts? The object's length that contracts is the object that is moving at the speed of light relative to the object that isn't. So here, this person isn't moving at the speed of light. So the length of the particle contracts because it's the object that moves at the speed of light it's going to seem to go through some sort of length contraction to the person who isn't moving at the speed of light, or the object that isn't moving at the speed of light. Okay? Does everyone understand how that works? So it's relative. The thing that experiences this length contraction is the thing that's moving at the speed of light, right? Relative to the thing that isn't. And who observes it? The person who isn't, the object that isn't moving at the speed of light, they observe the length contraction of the thing that is moving at the speed of light. Everyone good with that concept? You can say it again. Do you need it again, Jessica? Okay. If not, let me know. But right, so the object that's moving at the speed of light will always seem shorter to the object that isn't moving at the speed of light. That's how this works. The object moving at the speed of light will always seem shorter to the object that isn't moving at the speed of light. So nothing experiences the length contraction. Like the particle, when it feels the tube is shorter, the tube isn't actually shorter. Like if you were to go measure it, like if this person were to go measure it, they'd measure this length. They wouldn't measure the length the tubes, the particles measuring. The tube only seems that short because the particle, right, is moving at the speed of light. But it's in actuality, it's not that short. You see what I'm saying? Like if the tube's sitting still and the particle sitting still, it would be this length, its proper length right here. But since the tube appears to be moving at the speed of light to the particle, the tube seems to contract. It seems to get shorter to that particle at the speed of light. And it would measure it as that shorter, as that shorter length, right? Even though if it were to stop, it would go back to the original length. It would go back to proper length. Yes, Jessica. It's all just about observation. But here's the thing, maybe this is where we're getting confused, is that observation is the experience. Think of it that way. We're observing a shorter length and we're actually experiencing that as well. Does that make sense? Okay. All right, so it's 9. Again, he went on to a few other things. We can talk about it tomorrow. But those were the things he kind of jumped through. And again, we can talk about it tomorrow. I just don't want to keep you here any longer because we said we were only going to go till 9. So, but he also talked about the photoelectric effect, and then he went into quantum mechanics. But those are the only 2 things we didn't talk about. Again, if you want to talk about them tomorrow, we can talk about them tomorrow as much as you want. They're not meant to be very confusing. In fact, it's just like understanding the equation. Okay. Like for the photoelectric effect, do you at least know what's occurring there?
Yeah, the photoelectric is like frequency of some type of radiation, normally light, that hits a surface of metal that causes electrons to kind of like start bouncing off, not bouncing, like ejecting off of the metal surface.
Okay. I mean, yes, that is. Do you know why we're talking about it? Yes, that is it. That is it. That is it. What are we trying to show with it? What was the
Was it like energy emissions types problems?
no, it was I mean, yeah, I mean, yes. yeah, you can think of it that way. But Siley said light behaving both as particle and wave. So
Okay.
that's what it is, right? So the photoelectric effect is just trying to show you the light behaving like what? A particle or a wave? Which one is it?
Both.
No. So a particle, right? So the wave behavior we've actually talked about, right? Like when we talked about diffraction and interference, that bending, that's the wave function of a right? Like a photon can come in as a particle, which it would act just like a ball, right, of something. Or it could come in as a wave, and if it's a wave, right? And that's more what the Bohr model was trying to talk about. We can describe it a little bit different, but the photoelectric effect was specifically trying to describe the particle behavior of light, and essentially what it's showing is that the light, right? And this is the way this is that connection that he was making with intensity. So it was talking about these photons hitting, and essentially you can imagine the photon as like a billiard ball, and you can imagine the electron as a billiard ball. And when the photon hits that electron, it just like the two billiard balls hit each other and bounce off each other. That's what the electron and photon do. But what happens is that the photons can hit the electron so hard that it literally will eject them off the metal, like Eamon was saying, right? So it'll literally start to shoot those electrons off. And what do we call that? What do we call charges that are flowing? What do we call that?
Photons?
Like a flow of charge. So these photons are going to start to cause the photons. If we have this surface, and it has to be metal because these have to be delocalized electrons, but this photon is going to come in. It's going to hit, right? There's all these electrons here that are delocalized, and it's going to hit it, and it's going to, right, cause it to be ejected. And what do we call? So these are all charges. So what do we call charges that are flowing like that? It's current. So the photoelectric effect was trying to show you, I think he told you that the photoelectric effect is essentially how solar panels work. How we're able to take the sun, and the sun hits a solar panel, and it creates a current, and that current moves out of the solar panel, and then we could use that current to power our house, right? So that's what the photoelectric, like this is a photon, right? And then these are the electrons that are being ejected, and they're essentially being ejected by how hard these photons are hitting the surface. So that's all the photoelectric effect was trying to talk about, was this idea of the particles behaving like balls, like particles. And then the quantum mechanics, that's where we're trying to describe all this stuff in terms of waves. Like that's what quantum mechanics is essentially trying to when we talk about quantum mechanics, we're typically talking about like the wave function and things like this. So, but anyway, the one thing I'll say here to wrap it up is that these electrons for the photoelectric effect, since we ended up talking about it, are going to be ejected, right? And they're going to be ejected with a certain amount of kinetic energy. I'm going to need more room than right there. But these, as these photons come in, they're going to eject these electrons with a certain amount of kinetic energy. And so that's the equation that we gave you for this, where this is the kinetic energy of the photon that's ejected. I don't know why I'm abbreviating things. So kinetic energy of ejected electron. That's what this value is that you're calculating, is equal to this HF minus this BE, and this is binding energy. We'll talk about what all this. And another way to write that is the work function. So it can also be written in terms of phi, like the phi. This is the work function. But the work function is equal to the binding, so that BE is binding energy. So they're equal. Like you could write this either way. You could write it like that. You could write it with just the BE, or you could write it as just the phi. Like it means the same way. And then this is the way I'm more familiar with it, actually. But what are these things trying to explain to you? So I'm just going to leave this as phi. So this binding energy is the energy that the electron is bound to the surface with, right? So when the photon hits, the photon has to hit, right, with a certain amount of energy, and this energy right here has to be equal to stupid thing. So this right here is the photon energy. Okay. And this is the binding energy of the surface. So what happens is the kinetic energy. Sorry, my brain shut off for a second. I don't know what happened there. I'm so sorry. It's like looking at this and my words wouldn't come out of my mouth. And so what happens here is the kinetic energy of the ejected electron, right, is going to be like, there's going to be some amount of energy of this photon that's going to come in, but some of that energy of that photon is dedicated to just breaking the bond of the electron with the surface. And then the rest of the energy from that photon goes to the kinetic energy of that specific electron. Does that make sense what I'm saying? Good. Yep, you're good. Everyone, you can take
Yes,
off.
thank you. Thank you. I really appreciate it.
Yeah, I'm all done. I just wanted to say that one thing. I didn't mean to even say that. I meant to let you go 10 minutes ago.
No, you're good. No, you're good. You're good. You're good.
But I ended up talking about. But yes, have a great night. Please send me questions if you have them. And even if you have questions about this, I don't know why my brain shut off there. I apologize. But I'm proud of all of you. And please, if you have any questions, you can send them over email or whatever. And then also we're going to have that session tomorrow. So whatever questions you have, let me know.